Yeah, hi everyone. My name is Yohei. I'm a member of KUKAT Japan Research and Development Team, and I'm working on especially image recognitions here. So anyway, I'm going to talk about the evolution of CNN, convolutional neural network. So I hope almost all of you know the very basics of CNN. So I will skip the very basics, but I will introduce many models of CNN to you. But okay, let me begin with these interesting plots. So this blue line shows the number of papers, number of archive papers, which include the terms deep learning in titles or abstract in computer science region. And I did the same thing for the term CNN. So this is the orange line. So you can see that the number of papers of deep learning is rapidly increasing in recent years. And we can see the CNN is one of the major interests of deep learning research. Okay, note that this is very limited counting because some papers are not uploaded in archive and some paper does not include the term deep learning or CNN, but related to these topics. Anyway, this is the mainstream of recent deep learning or computer science research. So interesting. Okay, so today I focus on the CNN, convolutional neural network. And this is a brief history of CNN. Okay, you know there are many CNN models, so I picked up some important models and I introduced some their key concepts. So from the beginning, the neocognitron is the prototype of CNN, and then the Net5 and the most important model AlexNet. And after AlexNet, there are many models. So I picked up these models and introduced them. Okay, so the first, neocognitron. So do you know neocognitron? So this is the prototype of CNN, so which was introduced 1980. So surprisingly, so the year before I was born. So this is very surprise. Okay, now this is the prototype of CNN, and surprisingly, that this neocognitron has almost all important building blocks for current CNN. So this model has hierarchical structure, and it consists of S cells and C cells. So I skip the detail, but S cells is feature extraction. So this is corresponding to a convolution nowadays. And C cells is corresponding to average query. And then stack these layers like this. So this is almost the CNN. We know. So the only difference is how to train the weights. So neocognitron learning algorithm is self-organizing like training, not backpropagation. And probably you know the Cohen self-organizing map. So that is a kind of unsupervised learning of neural network, or for example the clustering also. So this neocognitron training is very similar to self-organizing map. So this is the beginning of CNN. And about 20 years later, the Net5 was introduced by Jan LeCun. So this model has three important points. One is convolution and subsampling. Last one is non-linearity. The convolution, okay, you know this is a very famous operation. So this convolution is like a feature extraction. And we have some muted region in the previous layer. And this area is related to some point on the next layer. And we, let's say, lambda these kernels of all images of it. It's convolution. And the subsampling. But this is so-called pooling nowadays. So this subsampling sampling is very easy to understand. So if we have this kind of feature map and some value, we just compute the average of some given areas. In this case, this colored region. So just the average. Then we get the smaller feature maps. And this subsampling gives the model with some positional invariance. So this means some small translation or rotation or scaling. So under these small transformations, the model is invariant because due to this subsampling. And last one is non-linearity. The non-linearity of LeNet5 is only introduced by this exponential function, tangent hyperbolic. So this is very simple. So just a monotonic increasing function. But if we stack these components like this, the model can extract a very complex nonlinear feature from the data distribution. So this is so surprising. Okay, so this is the LeNet5. And 40 years later, AlexNet appeared. So AlexNet has 4 important points that led rectified linear unit, max pooling, dropout, and GPU computation. Okay, first one, rectified linear unit. So this is very simple nonlinear function, so like this. So this is very amazing because this length keeps gradient alive. So in order to update the weights of neural network, we need some non-vanishing gradient. Okay, the learning algorithm of neural network is just gradient, back propagation. So this is some gradient of objective function. But this rectified linear unit, above this threshold, the gradient is always constant, so not vanishing. Then we can get some deeper architecture. And second one is max pooling. So in this case, we take just max value of this area. So in many cases, this max pooling is better than average pooling. And dropout. This is some generalization or regularization method. So we drop off some nodes probabilistically during training, and then model gets some generalization. So this is very simple but powerful method. The last one is GPU computation. So nowadays, almost all researchers who is studying deep learning, everybody uses GPU. So this is very important point of the research of CNN or deep learning. And this is the whole architecture of AlexNet. Just stacking the convolution and pooling and using dropout. Okay, this is a very basic architecture of CNN. Okay, the next one is networking network. So this model has 2 important points. One is multi-layer perceptron after convolution. And next one is global average pooling. So multi-layer perceptron after convolution is just like this. So usual convolution is just a linear transformation. But if we put between these layers, so this multi-layer perceptron can combine the feature of these convolutions, and we can train the weights of these multi-layer perceptrons weight by using ordinal gradient descent or back propagation. So we can get the efficient, complex combinations of these features. So this is one investment of networking network. But the more important point is this one, global average pooling. So this is one feature map for one each class. And networking network does not use fully connected layer. And do you know this global average pooling? This is a very important investment in CNN. Okay, this is but very simple. So if we like to classify some categories, for example, the 5 categories, we have 5 feature maps. And the average all over this one feature is here, the output of this node, so this category. And then we get we use softmax for getting probabilities for each class. Okay, so compared to free connect layers, this globalized querying can reduce the number of parameters drastically. So because the free connect layer has many parameters. Okay. For example, if input is 10,000 dimension and output is 10,000. Sorry. Input is 1,000 and output is 1,000. Free connect layer has 1 million parameters. So this is huge. But in this global querying, we just take average of these features. So no parameters here. And in this paper, they also reported this global average querying is better than the free connect layer. But I think this is not a general statement, so this is a special case. However, we should understand that this global average querying is important for parameter reducing. And then we get the very small model. So this case, 29 megabytes for ImageNet train model. So very small. Again, this is network. And VGG. VGG is deep model with basic building blocks. So VGG has no special building blocks. So this model uses only convolution, max querying, activation, free connected layer, and softmax. These are very basic components of CNN. But one important point is, VGG uses the sequence of small convolutions, especially 3x3 spatial convolutions. So before VGG, the CNN architecture used larger convolutions, like 11 by 11 or 9 by 9. But this VGG uses only 3x3 convolution, but stacks them. And this helps the model reduce the parameters. But VGG has many free connect layers. So 4,000, 1,000. So the VGG is a very big model, about several hundred megabytes. But the important point is here. They adapt the sequence of small convolutions. 3x3 convolutions. Then the insertion V3 here. I think all of you have heard this insertion V3. The basic building block is this inception module. And this module has parallel operations and concatenations. This is the input layer, this layer over one layer. Then parallelize some operations like this and use different filters. Then concat them and get next layer's output. It looks difficult or complex, but this inception module is so simple because they use mainly 3x3 convolutions here, 3x3, and usual querying. Our important point is the one-by-one convolution here. So do you know what is one-by-one convolution? So this is very important. So one-by-one convolution is applied to each pixel on the previous layer. So the difference is the change of numbers of channels. Feature maps has width, height, and channels. So this one-by-one convolution can change the number of channels. And this one-by-one convolution reduces the number of channels of this input. Then apply this 3x3 convolution. Okay, this operation, this inception module can reduce the number of operations, matrix operations, because we have smaller channels due to this one-by-one convolution. And this is so important point in recent CNN. And after some sucking this inception module, this inception module adapts global average querying and query connected. So the model take balance, accuracy, and model size. And finally, we get very good performance. So this is the inception V3 model. A very interesting module. Okay, next one is ResNet. So ResNet has leisure structure. So this is the this kind of bypass or shortcut connection. Okay, thanks to this shortcut connection, the gradient vanishing problem is partly solved because if gradient vanishes for this line, so this stacking line, but we can have also this gradient flow, non-zero gradient flow. So if the gradient vanishing for this line, but we have non-zero gradient flow like this. So we can put forward the gradient to the previous layer. So this is simple but very interesting structure. And this resonance also uses one-by-one convolution here to reduce the number of matrix operations. The efficient structure. Finally, this ResNet can be very deep. So in the paper, they also try to build more than 1,000 layers. But the best accuracy is achieved by this one, the 152 layers. But this is very deep. And this very deep structure can be achieved by this shortcut connection. Okay, this is the ResNet. And I think the best model of CNN nowadays is some combination of inception and ResNet, and so-called inception V4. This is the inception module and ResNet connection. Okay, the next one is SqueezeNet. This model aims to get this small model by using one-by-one convolution. And this SqueezeNet introduces so-called fire module. But this is very simple. So if you have this input, so you use one-by-one squeeze, so reduce the number of channels. Then take two operations, one-by-one expand and 3x3 convolution. Then concat them. So in order to reduce the parameter, you can use fire module. And also deep compression. This is done for lightening model size. So I will skip the details, but three important points: the sparse weight and weight quantization and Huffman coding to realize the efficient weight structure. So finally, we get the very small model. So using 6-bit data, it is a little bit strange, but we get the 0.5 megabyte. So small. And the important point is, one-by-one convolution. Okay, so I do not have time. So this is ENet. ENet is originally introduced for the real-time segmentation model, but the important point is same, one-by-one convolution. And the segmentation model is composed of two building blocks, the encoder and decoder. So we can use encoder as CNN by adding some global average query here. So anyways, init is also uses one-by-one conversion to reduce the number of parameters. And the deep complex network. So, okay, I will skip this. But nowadays, some researchers is interested to research the complex value networks, not real value. And it is said that this is some good advantage, but not confirmed, I think. So sorry, I do not explain due to the time limitation. And as a summary, we can compare the various models of CNN. So the vertical axis is accuracy, and horizontal axis is number of operations to inference one image. So you can see the inception before is the best model for accuracy, and VGG has very large operations, very large parameters. And so ENet or networking network is very small operation. So we can get small models for these. Okay, this is the comparison. And one funny comparison by, okay, this is the graph of accuracy per millions of parameters. So the accuracy for it, let's say this init is very good for this graph. So because the init is not bad accuracy, and very small parameters. So this using this percent per million parameters, so this init is the best model. This is funny, but I think interesting. So init and patch normalized network, and ResNet, and also VGG is a very large network. So not good for this graph. Okay, so this is the degree of some efficiency of the neural network. Okay, so that's all. Thank you.
Thank you. And also an overview of different models. Are there any questions?
Do you have an accuracy comparison for the SqueezeNet model?
Very good question. I do not have. But you can see the accuracy of SqueezeNet by checking this original paper. So let's check. Yes. But sorry, I do not have the graph of the comparison. Thank you.
I think it was around 70%.
Okay, so maybe 78%.
70.
So around here, I think.
Any more questions? Everybody's hungry, it seems. Can we say that complex neural networks can do both real images and imaginary images?
I do not know what is imaginary images because we can observe only real value. But in mathematical operation, we can consider this kind of imaginary operation. And interesting point is, I think, not CNN, but RNN. Some researchers reported this deep complex network gives better results of some recurrent neural network problem. But I do not know where.
Okay, thank you. Thank you. before we get on to the next talk, let's have a 10-minute break for socializing and eating.
Okay.